All right, let's dive right in and uncover the fascinating microscopic battles happening right inside your very own kitchen pantry. We often take for granted that our food just stays fresh, but the reality is every apple, every loaf of bread, and every single cut of meat is an active battleground. So today, we're decoding the science of food preservation in this explainer. We're going to look really closely at the exact scientific techniques we use to defend our global food supply. We've got a ton of ground to cover today, so here's our game plan. We'll start with the science of food spoilage, move into beating bugs with heat, look at cold preservation and slowing time, then starving microbes using water activity. Finally, we'll wrap up with chemical and biological defenses and some really cool modern innovations like hurdle tech. Let's get to it. Starting off with Section 1, the science of food spoilage, knowing the enemy. Now, you've probably faced this exact moment when opening your fridge and finding something a little questionable. What exactly turns a crisp, delicious apple brown or makes fresh milk go sour? Is it just a simple chemical reaction, a biological invasion, or just time taking its toll? Well, it turns out it's actually a combination of several invisible forces all working at once. Meet our spoilage villains. First up, we have our microscopic invaders, things like bacteria, yeast, and molds. These guys contaminate and literally consume our food, often turning into that fuzzy, forgotten science experiment lurking in the back of your crisper drawer. Then there's friendly fire. There are natural enzymes inside the food itself that trigger chemical breakdowns. This is exactly what causes an apple to brown or your veggies to get totally mushy. We're also battling oxidation, where the transfer of electrons actually causes fats to turn rancid. And finally, the visible invaders, insects and pests. All of our preservation methods are basically highly targeted countermeasures designed specifically to neutralize these threats. Moving on to Section 2, beating bugs with heat, which is essentially our lethal weapon. So the really crucial thing to understand here is that pasteurization uses super precise heat, always below 100 degrees Celsius, to completely wipe out disease-causing pathogens without actually destroying the food itself. For example, heating milk to exactly 72 degrees for just 15 seconds, that's enough to destroy incredibly tough pathogens like the tuberculosis bacteria, but it leaves the milk perfectly safe, liquid, and fresh. But, sometimes pasteurization just isn't quite enough. For much more aggressive defense, we seriously escalate the heat. We use a tactic called blanching. Think dropping peas into boiling water at around 88 to 99 degrees. This specifically targets and inactivates those natural enzymes we talked about earlier, stopping your vegetables from degrading over time. On the absolutely extreme end, we've got full commercial sterilization. By holding temperatures at 121 degrees Celsius for 15 minutes or more, usually using pressurized steam, we can completely annihilate microscopic invaders. Even incredibly resilient bacterial spores like Clostridium don't stand a chance. This right here is the exact science that makes canned goods shelf-stable for literal years. All right, on to Section 3, cold preservation, or as I like to think of it, slowing down time. So how do we actually pull this off? It all comes down to a physical cycle of heat removal. First, an evaporator absorbs the hidden heat energy right from inside your fridge. Then, a compressor does the heavy mechanical work to raise the pressure of the refrigerant gas. Next, the condenser physically pushes that trapped heat out into the surrounding air in your kitchen. Finally, an expansion valve drops the pressure to cool the liquid, and the whole cycle starts all over again. We aren't really adding cold, you see. We are meticulously extracting the heat. Now, it's absolutely essential to contrast how we use this extracted heat. Chilling, keeping things between -1 and 8 degrees, simply slows the spoilage reactions down. The microbes are still there, still active, they're just super sluggish. But freezing, dropping the temp to -18 degrees or lower, that's an entirely different ballgame. It physically locks up the water into ice crystals. Now here is the catch. The speed at which we freeze is absolutely critical. Fast freezing creates tiny little ice crystals, which preserves the delicate cellular structure of foods like strawberries or high-value fish. Slow freezing, on the other hand, creates massive, jagged ice crystals that literally rupture the cell walls, leaving you with totally mushy, ruined food when it thaws. Next up is Section 4, starving microbes, focusing on water activity. Here's a really fascinating fact. Microbes don't just care about how generally wet a food is, they care about how much free water is actually available to them. We measure this specific metric as water activity. By controlling this one thing, we are literally starving our microscopic enemies, totally cutting off the vital resource they need to multiply and survive. And we have several brilliant dehydration tactics to lower that water activity. There's traditional sun drying, physically evaporating moisture from things like leafy greens or ginger. Then we have high-tech freeze drying, also known as lyophilization. This is where we freeze the food and use a vacuum to sublimate the ice directly into vapor. This is actually how they make instant coffee that still retains all its incredible flavor. Finally, there's osmosis. When you pack fish in salt or make a super sweet fruit jam, the salt and sugar literally suck the free water right out of the microbial cells, leaving them dehydrated and dead. The goal across all these methods remains exactly the same: remove the free water. Okay, let's take a quick look at this table. We've just covered the thermal methods, like boiling, at the bottom, the cold methods, like refrigeration, and the physical dehydration tactics. So now, let's pivot and look at the top half to dive into the chemical methods of preservation, things like salting, sugaring, and synthetic preservatives. Which brings us right to Section 5, Chemical and Biological Defenses. Chemical defense is an incredibly delicate balancing act. Just look at these numbers for sulfur dioxide, which is super common in fruit juices. At a highly acidic pH of 2.5, you only need a tiny amount, about 200 parts per million, to stop yeast and mold in their tracks. But check this out. If the beverage becomes totally neutral with a pH of 7.0, you suddenly need drastically more. We're talking over 5,000 parts per million just to get that exact same defense. It really shows how much the chemical environment dictates who survives. But we don't just use chemicals, we also employ biological defenses, what I really like to call friendly fire. Through fermentation, we intentionally introduce specific beneficial starter cultures right into the food. As these good microbes multiply, they churn out organic acids, like the lactic acid in sauerkraut or kimchi, and they even produce antimicrobial substances. Basically, they outcompete the dangerous spoilage bugs and create a highly acidic environment where the bad pathogens just flat out cannot survive. All right, our final section, number 6, modern innovations and hurdle tech. Today, we are utilizing some truly space-age technologies to disrupt microbes. Take food irradiation, for example. By using ionizing radiation like gamma rays or electron beams, we can completely destroy pests and sterilize spices without applying a single drop of heat, a process some people call cold pasteurization. Then there's PEF, or pulsed electric fields. This applies a massive electric field that physically blasts open the pores in the cell membranes of bacteria, basically electrocuting them. It's an absolutely incredible alternative for pasteurizing fruit juices and prepping potatoes, letting us completely bypass traditional heat damage. And all of these individual tactics we've talked about, they culminate right here in something known as hurdle technology. Instead of relying on one massive extreme treatment, like boiling a food until all its nutritional value is totally destroyed, we stack multiple mild defenses. So we might slightly drop the temperature, lower the pH just a little bit to make it acidic, add a really mild chemical preservative, and then use vacuum packaging to suck out the oxygen. None of these hurdles would work perfectly on their own, but when you put them all together, they create an impenetrable, synergistic fortress. It guarantees absolute food safety while locking in all that amazing nutritional quality and flavor. So, what does this all mean for the future? As we push the boundaries of food science, moving all the way from ancient sun drying to literally electrocuting bacterial cell walls, I want to leave you with this thought. With all these emerging technologies, how will these invisible, microscopic battles continue to evolve the food on our plates? What is the pantry of tomorrow actually going to look like? Thank you so much for joining me for this explainer today. Keep your curiosity sharp, and I'll catch you next time.